Hello friends, in our last session on distance vector algorithm, we have discussed the basics along with one example. In continuation with the same, we will explore one more example for better understanding. Let us take yet another example for better understanding. Initially, all nodes have their distance estimates to the nearest neighbor. For example, here node A distance vector is shown. The DAA is set to 0 being a self node. DAB is having value 8. DAC, as there is no direct link between A to C, hence it is set to infinity. And likewise, for all other nodes, the appropriately the values are initialized. For the sake of to be very practical, a few asymmetrics were considered. Here, one of the link is missing, and this value is larger value among all these. All nodes then sends their local distance vector to their neighbors. Each and every node will send its own local distance vector to their neighbors. All nodes in turn receive distance vector from the neighbors. After receiving updates or the distance vector from the neighbors, these local nodes recomputes their distance vector. And after recomputing, they will then again send the recomputed updated distance vectors to their neighbors. Again, after receiving these recomputed updated distance vectors from neighbor, each node will then again recompute their distance vector and then sends the newly computed updated distance vector to neighbors. And this process will go on till either there is no change in the distance vector or there is node does not receive any updates from its neighbor. Now we will look at how the iterative computation occur at each node. Initially, the distance vector at node B is given at node A and at node C. These are the initial distance vector at each of the nodes A, B, C, and E respectively. Distance vector at A, distance vector at B, distance vector at C, and distance vector at E. Here the node B receives the distance vector from its neighbor. That is node B in receipt of distance vector from node A, node C, and node E. On receipt of the distance vector from all these three neighbors, node B will recompute its own distance vector accordingly. That is, on receipt of the distance vector updates from three neighbors A, C, and E, node B will recompute its own distance vector. The recomputation is shown here. dBA is 8, new dBC is 1, dBD is 2, likewise. And then it will update its own distance vector after recomputing. Next, as B's distance vector has been changed or updated, it will convey the updated distance vector to its neighbor. For example, here, suppose B is sending the updated distance vector of its own to the neighboring node C. On receipt of distance vector, updated distance vector from B, C will recompute its own distance vector. And it will update its own distance vector. Again, E will receive the distance vector, updated distance vector from its neighbor, that is from B, from D, from H, and from F. Likewise, this process will continue. This process of recomputing the distance vector at each node will continue till there is a change in its own local distance vector or it has received the updated distance vector from its neighboring node. This is how the distance vector algorithm works. When a node running the distance vector algorithm detects change in the link cost from itself to a neighbor, it updates its distance vector, and if there is a change in the cost of least cost path, it informs its neighbor of its new distance vector. Here given figure illustrates a scenario wherein the link cost from Y to X changes from 4 to 1. Here we focus only on Y and Z's distance table entry to destination X. The distance vector algorithm causes the following sequence of events to occur. At time t0, Y detects the link cost change. That is, the cost has changed from 4 to 1. It updates its distance vector and informs its neighbor of change, that this change since its distance vector has changed. At time t1, Z receives an update from Y and it updates its table. It computes a new list cost to X, which in our case has decreased from 5 to 2, and sends its new distance vector to its neighbor. At time t2, Y receives Z's update and updates its own distance table. Y's least cost do not change. Hence, Y does not send any message to Z. Hence, the algorithm comes to an wait state. Thus, in this case, only 2 iterations are required for distance vector algorithm to reach to an wait state. Good news about the decreased cost from between Y and X, that is from 4 to 1, has propagated quickly through the network. Now let us consider what happens when the link cost increases. Earlier we have seen that the link cost was decreasing from 4 to 1. Now we will consider it another example wherein link cost is increasing. Here from 4 to 60. Before the link cost changes, dy of x is 4, dy of z 1, dz of y is 1, dz of x is 5. At time t0, y detects the link cost change. That is, the cost has changed from 4 to 60. Hence, y compute its own minimum cost path to x. That comes out to be 6. Of course, with our global view of the network, we can see that this new cost via Y is wrong, Y Z is wrong. But only information node Y has, it has that its direct cost to X is 60, and that Z has last told Y that Z would give to X with cost of 5. As of time T1, we have a routing loop in order to get X, Y route through Z and Z route through Y. The routing loop is like a black hole. A packet destined for X arriving at Y or Z as of T1 will bounce back and forth between these two nodes forever. Since node Y has changed and computed a new minimum cost to X, it informs Z of its new distance vector at time T1. After time T1, Z receives Y's new distance vector, which indicates that Y's minimum cost to X is 6. Z knows it can get to Y through a cost of 1 and hence compute a new least cost to X, which is 7. In similar manner, after receiving Z's new distance vector, Y determine dy x as 8 and sends Z its new distance vector. Z determines dx as 9 and sends Y its new distance vector, and so on. One question arises here. How long will the process continue? Here the loop will persist for 44 iterations, message exchanges between Y and Z, until Z eventually compute the cost of its path via Y to be greater than 50. At this point, Z will finally determine that its least cost path to X is via its direct connection to X. Y will then route through X via Z. The result of bad news about the increasing link cost has indeed traveled slowly. If there is a large variation in link cost, such a scenario may lead to one problem, which is sometimes referred to as Count infinity problem. Distance vector and link state algorithms take complementary approach towards computing routing. In distance vector algorithm, each node talks to only its directly connected neighbors, but it provides its neighbor with least cost estimates from itself to all the nodes that it knows about in the network. Whereas in link state algorithm, each node talks to all other nodes via broadcast, but it tells only the cost of its directly connected link. We will conclude our study of link state and distance vector algorithm with a quick comparison of some of the important attributes like message complexity, speed of convergence, and robustness. Recall that N is the set of nodes, that is router, and E is the set of edges, that is links. What can happen if router fails, misbehaves, or sabotage? Under link state, router could broadcast an incorrect cost for one of its attached link, but no others. A node could also corrupt or drop any packet it received as a part of a link state broadcast. But and linked state node is computing only its own forwarding table. Other nodes are performing similar calculations for themselves. This means root calculations are somewhat separated under linked state, providing a degree of robustness. Under distance vector, a node can advertise incorrect least cost path to any or all destinations. More generally, we note that at each iteration, node's calculation in distance vector is passed on to its neighbor and then indirectly to its neighbor on next iteration. In this sense, the incorrect node calculation can be diffused through the entire network under distance vector. As far as message complexity is concerned, we have seen that least state requires each node to know the cost of each link in the network. This requires BGO, mod N and mod E messages to be sent. Also, whenever a link cost changes, the new link cost must be sent to all the nodes. Distance vector algorithm requires message exchange between directly connected neighbors at each iteration. We have seen that the time needed for algorithm to converge can depend on many factors. When link cost changes, the distance vector algorithm will propagate the results of the changed link cost only if the new link cost results in changed link least cost path for one of the nodes attached to that link. As far as speed of convergence is concerned, we have seen that our implementation in link state is an BGO and square algorithm requiring BGO mod N into mod E messages. In distance vector algorithm can converge slowly and can have routing loops while the algorithm is converging. Distance vector also suffers from count to infinity problem. In the end, neither algorithm is an obvious winner or the other. Indeed, both algorithms are used in the internet today. Here we have covered the details of distance vector algorithm. Next, we will cover other routing algorithms like OSPF, RIP, and BGP in our next session. Thank you.